Start the recording, and then I am going to share my screen, so just give me a moment again. Okay. So specifically, I gave you an extra problem to do in that 6.2, but when you approach these problems, what I would suggest you do is to, the irritating thing when you start these problems is, for instance, if I now have the volumetric rate. So the volumetric rate in that 6.2, hopefully you're aware that we're busy with the volumetric rate that stays constant. I have my two equations that gives that volumetric rate, the area-based mass-based rate, mass transfer rate constant, the conversion factor, and that first order concentration dependence of that part of the rate. Then, on the other side of the equation, I have and let's start the whole train. I have my site-specific rate constant. Then I have how many sites do I have per active area. In this case, it is a solid catalyst. So I have AM over there to convert it to KI dash. So this will give me KI dash, right? KI dash. This, once again, will give me KI double dash, right? And now I want it to be on a volumetric basis. So for a CSCR, I have to multiply it by the amount of catalyst that is in my reactor. And then, of course, it is second order. So this is the concentration dependence. So now you were given information at a specific scenario for KI dash, okay? And now you can look at this, what you've written there, and say, okay, if anything there changes, my KI dash, okay, there's just a single dash there. Now my KI dash is going to change. So I didn't change the type of catalytically active sites that I didn't change the load. And in the first part of that 6.2, the original part, I also didn't change AM. Because AM depends on the catalyst density, and it is inversely proportional to my particle diameter. But I didn't change my particle diameter in the first part of that TUT. Okay, so but what I am changing is I am changing KC. Right, so I'm changing KC, and now I just need another reminder on this side. So the KC changed because I told you this thing is directly proportional to the RPMs in this reactor. I now also gave you additional information. I say, all right, it's not only directly proportional to, the RPMs in the reactor, it is inversely proportional to, or not completely inversely, it's got this weird dependence on the particle diameter, my Kc. Kc will always change with RPMs and with dP. Okay, so now I know if anything in this group of terms change, my Kc will change accordingly. Now, if I evaluate my AC, what is that proportional to? That is going to be proportional to, and you now need to inspect that. It's proportional to AM times CCAT for a CSTR. And AM times CCAT is proportional to inverse of the particle diameter times CCAT. So if any of these variables change, my AC changes. Okay. So what many people neglect when they attack the first part of that 6.2. In the first part of that 6.2, the diameter stays the same. So if I now, and now the uncomfortable part of this problem is that you do not have enough information to calculate AC explicitly or KC explicitly. And you do not have information on the L of the sites. But this is where you now are going to modify your equations to say, okay, now I can write it in terms of, so if I have a KCAC at any new situation, if I want to calculate it, it will therefore be equal to the KCAC at my old situation where you have a variable available for it. And now I multiply it by RPM new, dP to the power of min 0.7 new, CCAT new, divided by RPM old, dP old to min 0.7. C cat old. And on the other side of my equation, I do exactly the same if I now want to substitute my Ki, the volumetric rate constant. Okay, so I'm going to, so what will happen is that some variables will cancel out, this you know, some variables will cancel out, some will stay the same. What you need to understand is that this changes, okay, let me just get a red, this changes in the first part of the TUT, the official parts of the TUT, that CCAT changes, and the CA surface changes. So in this single equation, as I've written it here, I've got two unknowns. I need an extra equation, and that is just either this one, where I know the value of my volumetric rate, or the one where I know that it's equal to my Ki, the volumetric rate constant, which is equal to all that stuff multiplied by CAS squared. Right, so these are the two equations you have to solve simultaneously. Substitute this as in terms of just the symbols, yes, substitute it symbolically and then just see what happens. Sometimes, you know, if you substitute that, you will actually see that on this side I've got a CCAT old and a CCAT new ratio, and that will cancel out. So the CCAT cancels out in this part of, if I want to solve it by hand or I want to solve it sequentially, I can solve that CA surface easily first, and then substituting the CA surface in there, I can solve my new volumetric rate constant and I can solve for CCAT. Okay, so that is now, this is actually the problem solved, right? But I would like you to apply it in that 6.2 and of course finish that 6.3. And also, please, 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 try to generate the following. Try to generate the following. I want a figure of how CCAT changes with RPMs, and I want a figure that shows how CCAT changes with particle diameter, right? And make that particle diameter really small. Make it really small and make it, let's say, go to double the size range, 2 times the dP value. So we will give you answers just to make sure that you are correct for that extra question I asked, where I said, okay, now, in case you missed the extra question, so the extra question on that 6.2 you can find in the ClickUp announcement. That will not disappear. But what I ask you to do is keep the RPMs constant at that initial 200 value. But now, change the particle diameter. So your new particle diameter is half of your old particle diameter. Okay? So you don't really specifically need to know the value of that particle diameter. You just need to know what is that ratio, because in here you can write that as a ratio. Please don't get stuck because you cannot. You want to calculate that value explicitly. You do not have enough information, but in prorating situations where you don't have enough information, but at least what you do know is what is the dependence of my parameters on specific variables. So I want you to plot that, and I want you to generate figures where you plot CA surface as a function of these variables and see what happens. See what happens to your CA surface. Does it approach CA bulk? At a certain point, you can make this smaller and smaller and smaller, and it's not going to make a difference. And at a certain point, you're going to make this larger and larger and larger, and it should not make a difference. And then, where we are then is finally where before we started Theme 6, is when I can say, all right, you can now neglect that because this difference becomes negligible. But please see whether you can apply your skills to discover that for yourselves. Right, so this is what I wanted to say. Let me just stop sharing my screen and see if there are any questions in the discussion. Just good mornings. Right, people in the room, in the virtual room, any questions? Or in the real room, any questions at this stage that you want to type? Just put up your hand and I will wait before I leave the platform. Okay, so yes, think of, as I suggested, if you're done with this TUT, you're welcome to proceed to TUT 7, or you may ask yourself what will happen if I change the temperature between the different runs. Maybe not, using the energy balance and this simultaneously, so not the integrated kind of question. That is not what you can expect in the semester test. In the semester test, you will have separately, so when you attack the CSTR equilibrium problems, prepare for that again for the semester test. Please note that for that part of the work, the STEAM 5 part, CA bulk is equal to CAS, and we don't have any internal diffusion limitation. So it is as if our CA surface is equal to CA bulk, and the eta, the effectiveness factor of my catalyst particles, if it's catalyzed reactions, will be equal to 1. Right, any questions for now? Once again, going. Okay, the recording will be stopped.